So section 4.8 covers the Hopi-Tau's rule. And the Hopi-Tau's rule is really useful because it allows us to evaluate more limits than we could before. So the Hopi-Tau's rule, what it does is it uses derivatives to calculate limits when we're given indeterminate forms. This allows us to evaluate more limits than before, as we no longer have to rely on numerical evidence. Using this rule, we can definitively show a limit exists and finds its value. So we've got a lot of indeterminate forms. I could have 0 over 0, infinity to the 0, infinity over infinity, 1 to the infinity. So these are examples of indeterminate forms. So we're going to solve a bunch of examples using the Hopi-Tau's rule. So here what I have, if I have a function and the limit goes to a, and I have an indeterminate form, I can take the limit of, as x goes to a, of the derivative of the numerator over the derivative of the denominator. Special note, we are not using quotient rule. We are not using quotient rule. We're treating our numerator and our denominator separately. So let's take a look at this first function. I have the limit as x goes to 2 of x squared minus 4 over x minus 2. And what I want us to do is I want us to take the derivative of the numerator and the derivative of the denominator. Again, we are not using the quotient rule. So that gives me 2x over 1. So I have the limit as x goes to 2 of 2x. Well, that's just going to be 2 times 2, which is 4. So now, using this rule, we were actually able to evaluate this limit. Let's try this again. I have a limit of 1 minus cosine of x over x. Well, the cosine of 0 is 1, so I get 1 minus 1, which is 0. 0 divided by 0, that's an indeterminate form. So we need to take the derivative of our numerator and of our denominator. The derivative of 1 minus cosine is just going to be sine of x over 1. Well, the sine of x as x goes to 0 is just 0, so 0 over 1 is 0. Now, I didn't say that using Hopi-Tau's rule we'd always get something that wasn't 0, but at least we were able to solve this one. Next, I have the limit as x goes to the limit of sine of x over x. So I need the limit as x goes to 0, cosine of x over 1. As x goes to 0, I get 0 over 1, which is, as x goes, cosine of 1 is 1, so I get 1 over 1, which is 1. Hooray! Let's try a couple more complicated examples. So I have the limit of e as x to the infinity of e over 1 divided by x minus 1 over 1 divided by x. Again, we have the form 0 over 0. So I have the limit, if I take the derivative of the numerator and the derivative of the denominator, as x goes to infinity, of e to the 1x negative 1 over x squared over negative 1 over x squared. These are going to cancel. So I have the limit as x goes to infinity of e to 1 over x. Well, as x goes to infinity, 1 divided by infinity is going to be really, really close to 0. So I have e to the 0 power, and any number to the 0 power is just 1. Next, I have the limit as sine of x minus x over x squared. So we're going to apply the Hopi-Tau's rule. That gives me cosine of x minus 1 over 2x. But I have a problem here, right? This is still an indeterminate form. I still have 0 over 0. So I'm going to need to take the second derivative. It's nice to know we can apply the Hopi-Tau's rule multiple times. So now if I take the limit as x goes to 0, that gives me negative sine of x over 2. Sine of 0 is 0, so I get 0 over 2, which is 2. Our next indeterminate form is infinity over infinity. So as you can see by looking at this first equation, if I plugged in infinity, I'd get infinity over infinity. That's not cool. So I need to take the derivative. That means I have the limit as x goes to infinity of 3/2. So my answer is just 3/2. Next, I have the limit as x approaches 0 from the right for the natural log of x over the cotangent of x. And I'm going to take the derivative of this. So I get the limit as x approaches 0, 1 over x negative cosecant 2x. Now what do I do? Well, now as x approaches 0 from the right, cosecant squared approaches infinity. So anything could happen with the product of these derivatives. So what I want to do is I want to rewrite using the fact that cosecant is 1 over sine. So here I have 1 over negative x cosecant squared x. And I'm going to rewrite this using 1 over sine. Well, I've got 2 signs in the denominator, so that means I'm going to have negative x over sine squared of x. And now I can take another derivative. This gives me the limit, sorry about the messiness guys, as x goes to 0 of 2 sine cosine x over negative 1. That's going to be 0 over negative 1, which is 0. So our limit in this case was 0. This next example is a little bit simpler. I'm going to change colors so we can see what's going on. I'm going to take the natural log of the derivative of the numerator over the denominator. So I get 1 over x divided by 5. That's 1 over 5x. As x approaches infinity, I get 0. We can also use the Hopital's rule to evaluate limits of other indeterminate forms. Here are a few of those types of forms we could look at. So let's work at some examples where I have 0 times infinity. So here's what happens. As x approaches infinity, this goes to infinity, and this goes to 0. So I'm going to take the limit as x goes to infinity. That's going to give me 6x over 2x. Well, as x goes to infinity, that's going to be 6 over 2, which is 3. For my next one, I still want to take the derivative of the numerator over the derivative of the denominator. So I have the limit as x goes to infinity of 6x over 3x, which is going to simplify down to, 3x squared. That gives me 3 over, that gives me 2 over x. Well, 2 divided by infinity is going to go to 0. Next, I have the limit of x natural log of x. X goes to 0. Natural log of x goes to infinity. But first, we need to rewrite as a quotient. So I'm going to rewrite this as the natural log of x over 1 over x. And now we have to exhaust it from the right because as natural log goes to infinity, 1 over x goes to infinity as x goes to 0 from the right. So I have natural log of x over 1 over x. That gives me 1 over x over 1 over x squared. So I need to take the derivative again because now I have infinity over infinity. This is going to give me the limit as x goes to 0 is now negative 1, which is just going to be 0. Final answer. Next, I want to look at the indeterminate form of of infinity minus infinity. Right? This is a little bit different because it isn't written as a quotient, but here I'm going to get 0 minus infinity. So what I need to keep in mind